All right, so today we're going deep on machine learning security,
Okay.
specifically data poisoning attacks.
Interesting.
And we're going to be looking at these in the context of online learning.
Yeah, that's a very important area.
Yeah, and to help us unpack all this, we've got this paper by Wang and Chaudhuri.
Oh, yeah, I've seen that one. That's a good one.
It's a really good one, very interesting. So
It really digs into the nuances of the problem.
yeah, so before we jump into that,
Okay.
just to set the stage a little bit for our listeners,
Right.
we're going to be focusing on binary linear classification
Okay.
in an online setting.
Right.
So maybe you could start by just reminding everybody what makes this different from the offline scenario.
Sure. Yeah. So the key difference is really in the nature of the data.
Okay.
So in offline learning, you have a static data set, right? You train your model on that and you're done.
Right.
But in online learning, things are a bit more dynamic.
Okay.
The data comes in sequentially.
Like a stream.
Yeah, like a stream, exactly. So the model is constantly learning and updating
Interesting.
as new data points come in.
So it's like it's always adapting,
Exactly. Yeah, it's a much more dynamic process.
which I guess makes it more powerful in a way.
It does. Yeah, it allows the model to adapt to changing patterns and new information.
But it also, I guess, opens up more vulnerabilities potentially.
That's right. Yeah, and that's where these data poisoning attacks become really interesting
Okay.
because now the adversary can kind of inject these malicious data points into the stream.
And manipulate it.
Yeah, and manipulate the learning process as it unfolds.
And the paper specifically looks at two online settings,
Mm,
the semi-online and fully online.
right.
So could you maybe just quickly walk us through the distinction between those two?
Sure, yeah. So in the semi-online setting, the attacker is really focused on the final classifier.
At the end.
Yeah, the one you get at the end of the training.
Okay.
So it's kind of like poisoning the well so that the final product, the final classifier, is tainted. Whereas in the fully online setting, the attacker is a bit more ambitious.
Okay.
They're trying to actually degrade the performance over the entire learning window.
So the whole process.
Yeah, the whole process, not just the end result.
So it's like a more ongoing,
It's a more insidious attack, yeah.
Yeah.
It's about disrupting the learning itself.
gotcha. So we've got these two different settings.
Right.
And the paper looks at three different attack methods.
Yes.
And all of these are aimed at maximizing classification error.
Yes, that's correct. Yeah, that's the attacker's goal in this case.
And that's what we're going to be unpacking today.
Yeah, we'll dive into how these methods work
Yeah.
and what makes them effective.
Now, before we get into the methods themselves,
Okay.
let's talk about the adversary.
All right.
We're working, I guess, with this assumption of a white box adversary.
Right.
So what does that actually mean?
So in this setting, the white box adversary is assumed to have complete knowledge of the learning algorithm, the model parameters, the data stream, even the defenses that are in place.
So they basically have full visibility.
Yeah, they have pretty much full access to the system.
Now, that seems like a pretty strong assumption.
It is a strong assumption.
So why make that assumption?
Well, the idea is to design defenses that are robust,
Right.
even in the worst case scenario.
Okay, so you're basically assuming the worst and you're trying to prepare for that.
Exactly. Yeah, because relying on security by obscurity, hoping that the attacker doesn't know certain things, that's never a good strategy.
Right.
It's much better to be over-prepared.
Yeah. Better safe than sorry.
Exactly.
Now, the attacker, even though they have all this knowledge,
Right.
they're not all powerful.
That's right.
They can modify a limited number of examples, right?
Yeah. There's a budget, so to speak, on how many points they can modify.
Okay.
And there's also this constraint in place called the feasible set defense,
Okay.
which prevents them from injecting like totally arbitrary outliers.
Mm-hmm. So they can't just completely...
They can't just, completely break the system. It
Yeah.
forces them to be a bit more subtle.
So it's like a game of subtle manipulation.
Exactly.
Okay.
It's not brute force.
So how do they actually go about this?
Right.
How do they, given that they can only change a certain number of points,
Right.
how do they optimize those changes
Right.
to maximize that classification error?
So that's where the real challenge lies, right?
Okay.
Because solving this optimization problem in an online setting is much trickier than in the offline case.
And why is that?
Well, in online learning, the order of the data matters.
Okay.
The model is constantly updating, right,
Right.
based on what it sees.
Like it's learning as it goes.
Exactly. So the attacker needs to consider not just what to modify, but also when to modify it within the stream.
Oh, So the timing.
The timing becomes crucial, yeah.
It's super important.
Because a data point introduced early on could have a cascading effect.
Oh, interesting.
Yeah, it's like a ripple effect through the whole learning process.
Okay, so they've got to be really strategic about it.
You have to be very strategic, yeah.
All right, so let's, now that we've kind of set the stage, let's
All right.
actually get into these attack methods.
Okay.
And see how they play out. So we've got these 3 attack methods that we want to look at.
Right.
What's the first one? How does this work?
So the first method is called the incremental attack.
Okay.
And it's essentially a greedy approach
Okay.
where the attacker at each step is going to select the training point that, if modified, would have the biggest impact on their objective.
Okay, so like the most bang for their buck.
Yeah, exactly. They're trying to be as efficient as possible with their modifications.
So how do they figure out which point to change?
Right. So they'll compute the gradient of their objective function with respect to each training point,
Okay.
and then they just pick the one with the highest magnitude.
So the one that if they tweak it,
Yeah.
it's going to move the needle the most.
Yeah, exactly. They're looking for the steepest ascent towards their goal, which is maximizing the classification error.
Okay, so they change that point and then they just keep going.
Right. They move on to the next iteration and repeat the process.
Always looking for the next most impactful point.
Exactly.
Now, this sounds pretty straightforward,
Yeah.
but are there any drawbacks to this approach?
Well, the main limitation is that, like all greedy approaches, it can get stuck in local optima.
Okay.
So they might find a point that seems really impactful locally,
Right.
but it's not necessarily the best choice globally if you consider all the possible modifications they could make.
So it's like they're climbing a hill,
Yeah.
but they might end up on a small peak.
Yeah, exactly. A small peak when there might be a much higher mountain somewhere else.
Right, right. Okay, so that's the incremental attack.
Right.
What about the next method? Does it address that that problem of local optima?
So the second method, called the interval attack,
Okay.
takes a different approach. Instead of modifying individual points scattered throughout the stream, it focuses on finding the best consecutive sequence of points to modify.
Oh, so they're looking for a whole chunk of data.
Exactly. They're trying to find an interval of points where if they modify all of those, it'll have the biggest effect.
Right.
And this approach is particularly effective in the semi-online setting.
Okay, and why is that?
Because remember, in the semi-online setting, the attacker's goal is to manipulate the final classifier.
Right, right. The one at the end?
So by targeting a concentrated portion of the stream, they can have a more focused impact on the model's final state.
So it's like they're really trying to steer the model in a particular direction?
Yeah, they're trying to make sure that the model ends up in a state that benefits them.
Okay, so that's the interval attack.
Right.
Now, what about the fully online setting?
Right.
Where the attacker's trying to disrupt the learning all throughout?
That's where the third method comes in, called the teach and reinforce attack. And this one's a bit more sophisticated.
Right.
It splits the attacker's budget into 2 parts.
Okay.
First, they modify some initial points to kind of teach the model the wrong behavior.
Okay, so they're like setting it off on the wrong foot.
Exactly. They're poisoning the well at the source.
Right.
And then they use the remaining budget to reinforce this wrong learning
Okay.
by strategically modifying points throughout the rest of the stream.
So it's like a 2-pronged attack.
It is, yeah.
They're not just trying to introduce noise. They're actively trying to guide the model towards a bad state.
Precisely. They're exploiting the model's adaptability to make it learn the wrong thing and then make sure it keeps learning the wrong thing.
And how do they decide how much budget to allocate to each part?
So they have this hyperparameter alpha that controls the split,
Right.
and they typically find the best alpha through a grid search or something similar.
So they're basically experimenting to see what works best.
Yeah, exactly. They're trying to optimize their attack strategy.
Okay, so we've got these 3 different attack methods.
Right. Each with their own kind of approach.
Yeah.
But how do they actually perform? Like, did the researchers test these out?
They did, yeah. They conducted a bunch of experiments
Oh.
on different data sets to see how well these attacks work in practice.
Like what kind of data sets?
So they used a synthetic data set,
Okay.
M&S, Fashion M&S,
Okay.
and also the UCI spam base data set.
So good mix.
Yeah, a good variety of data sets to test the generality of their attacks.
And what did they find?
So the main finding was that the online attacks, these 3 that we discussed,
Okay.
consistently outperformed the oblivious baselines.
Okay, and what do you mean by oblivious baselines?
So these were attacks that didn't take into account the sequential nature of the data.
Okay.
So for example, just randomly flipping labels
Right.
or using an offline attack method.
So those didn't work as well.
No, they were much less effective.
So it really highlights the importance of understanding the dynamics of online learning. Absolutely. If you're an attacker, knowing how the model is learning and adapting gives you a huge advantage.
Right. Okay, so these online attacks are more effective.
Yes.
What else did they find? Anything interesting about like where in the data stream the attacks were most effective?
Yeah. So they found that the best positions to attack actually varied,
Oh, okay.
depending on the online setting and the learning rate being used.
Oh, interesting. So it's not just about what you change, it's also about when you change it.
Exactly. The timing is crucial.
And how did the learning rate come into play?
So they looked at different learning rate schemes,
Uh-huh.
like constant slow decay and fast decay.
Okay.
And what they found was that the fast decay learning rate,
Okay.
where the model makes big updates early on and then becomes less sensitive to new data,
Uh-huh.
was particularly vulnerable to these online attacks.
So like the model is really impressionable in the early stages.
Exactly. And the attackers can exploit that.
Wow. So we've got these different attack methods.
Right.
We've seen how they perform. But what about defenses? Like, what can we actually do to protect ourselves from these attacks? So given all these vulnerabilities, are there any ways to actually protect our models?
Yeah, so the paper does suggest some interesting directions for defenses.
Right.
One key idea is to use online learning algorithms that are less sensitive to individual data points.
Okay, makes sense. So if a single point is corrupted,
Right.
it doesn't completely derail things.
Exactly. Yeah. And one specific example they mention is averaged stochastic gradient descent.
Okay.
So instead of relying only on the current model parameters,
Uh-huh.
it actually averages the parameters over like a window of past iterations.
Oh, so like it has a memory.
Yeah, exactly.
Yeah.
It's like a smoothing mechanism
Okay.
that makes it less susceptible to sudden shifts caused by a few bad data points.
So it's more robust.
Yeah, exactly. More robust to those adversarial perturbations.
Now, another thing I've heard about is adversarial training.
Right?
Could that be applied here?
Yeah, absolutely.
How would that work?
So in adversarial training, you basically train the model on examples that have been intentionally corrupted.
Oh, interesting.
It's like giving the model a vaccine. You're exposing it to a weakened form of the threat,
Right.
so it can learn to be immune to it.
So in this context, we'd be training on data that's been poisoned.
Exactly. You could use these methods we discussed to generate poison data and then train the model on that.
And that would hopefully make it more resistant.
Yeah, the idea is to force the model to learn features that are more robust,
Good.
that are not easily fooled by these adversarial manipulations.
That's really clever.
And then, of course, there's also the whole area of data preprocessing and filtering.
Right. So we can try to catch these bad points before they even get to the model.
Exactly, yeah. So things like anomaly detection,
Okay.
statistical analysis of the data,
Uh-huh.
even using external knowledge about the data distribution to identify outliers.
So it seems like there's no one silver bullet.
Yeah, there isn't.
It's really a multi-pronged approach.
Exactly. You need a combination of robust algorithms,
Right.
adversarial training, and then good data hygiene.
Like a defense in depth.
Exactly. And
Okay.
especially in online learning where things are constantly evolving,
Yeah.
you need to be proactive.
Stay ahead of the attackers.
Exactly. It's a constant arms race.
Well, this has been really eye-opening.
Yeah, it's a fascinating area.
It's made me think about online learning in a whole new way.
I think the key takeaway here
Yeah.
is that security can't be an afterthought. It has to be baked into the design from the beginning.
Absolutely.
You have to anticipate these attacks and be prepared for them.
Well, on that note, I think we've reached the end of our deep dive.
Yeah, I think we've covered a lot of ground.
We've learned a lot about these data poisoning attacks.
Absolutely.
And how to potentially defend against them.
It's all about understanding the vulnerabilities.
Right.
And then designing systems that are resilient to them.
To our listeners out there,
Yes.
we encourage you to delve deeper into this research.
There's so much more to explore.
This is just the tip of the iceberg.
Absolutely. And as online learning becomes more and more prevalent,
Yeah.
understanding these security challenges is going to be more critical than ever.
So stay curious
Be vigilant.
and keep learning.
Absolutely.
And until next time,
Happy learning.
happy learning, everyone.